So here's where we were last time. End of chapter 2. It's not really the end of chapter 2. Griffiths doesn't talk about it in chapter 2, but there's so much stuff going on at the beginning of chapter 3 that I thought it was good to sort of make some analogies. Just after we've seen the collection of examples in chapter 2, it's good to make analogies between what we see in the continuous and discrete energy spectrum case. So this is stuff we wrote on the board last time. If the potential, oops, that's not what I wanted to do. If the potential has a discrete energy spectrum, like we saw in the infinite square well and the harmonic oscillator, that's the case we're all familiar with, right? We can write any normalizable state at a certain time, we usually think of it as an initial time, as a linear combination of the energy eigenstates. And those energy eigenstates are an orthonormal collection. In other words, if I normalize each one of them, then the integral of psi n star psi n dx is 1. And it turns out they're mutually orthogonal to each other. So that's an orthonormality relationship. We write it as the Kronecker delta function. And we can use those to solve for the CNs, like we've talked about several times now. Furthermore, there's an interpretation of the magnitude of Cn squared as representing a probability of measuring a certain energy, En, right? So here's the analogous things. Without proof, there's a little bit more proof in the way of the notes. But in the cases that we've seen, like for the, the easiest case is the free particle, but then we had the Dirac delta function potential had mostly a continuous energy spectrum, and so did the finite square well. There we have a continuous collection of energy eigenfunctions. None of them are normalizable, right? We said from k equals minus infinity to infinity. For the free particle, these were our e to the ikx's, right? They're a complete collection. Complete just means you have enough of them so that you can write an arbitrary normalizable function as a linear combination of those. The coefficients here I'm writing is a of k. If for the free particle, we might have written that as phi of k with an extra 1 over root 2 pi out in front. But there's some coefficients, right? And the question is, well, what is the analogy to orthonormality? Well, they're not normalizable, these functions, the psi k. What can that possibly mean? And it means that we can put a number out in front of those e to the ikx's, say in the case of the free particle, such that the integral of psi k prime, psi k prime star, is delta of k minus k prime. A Dirac delta function rather than a Kronecker delta function that we saw up there. And what that means is we can use that the Dirac orthonormality condition. So we'll call the collection Dirac orthonormal. If we bother to put a normalization constant in front of this, that doesn't normalize the function, but it makes it so that this is true. So it's like we've chosen a normalization constant even though they're not normalizable. And in that case, we can solve for the a of k's exactly the same way we solve for the CNs up there, by taking the original condition, the completeness condition, I just wrote it out down here in the non-blanked out stuff, multiplying by psi k prime star and integrating with respect to x. We see a delta function here which kills off one of the integrals, and then the delta function itself makes the second integral go away, and we're just left with a of k prime, and that gives us a formula for a of k prime. Furthermore, we've talked about the probability density as a function of x, but this, I'm just saying this without proof now, and it's actually going to be part of our postulates when we get into the postulates in chapter 3, that the magnitude of those expansion coefficients, magnitude of a of k squared, is the probability density as a function of k, as a function of wave number. And a similar thing is going to go for momentum and energy, so if we can we'll be able to get rho as a function of just about anything. So that's what we talked about last time. Kind of a busy slide, but we built it up piece by piece. Okay, so again, a collection is orthonormal if it satisfies this Kronecker delta kind of condition. It's Dirac orthonormal, and we usually say with respect to a certain parameter, here our parameter is the wave number, if this integral gives delta of k minus k prime. Notice that since k is equal to root 2 me over h bar if I substitute what k and k prime are in terms of e and e prime. This would not give delta of e minus e prime. So it wouldn't be Dirac orthonormal with respect to the other ones. So for example, if we take the case of the free particle, it's not too hard to see what the Dirac orthonormal collection has to be. Those mysterious 1 over root 2 pi's that we saw out in front in the statement of the Fourier-Plancherel theorem, we just associate them with the e to the ikx and e to the minus ikx in those two formulae, and we'll find out that this collection has the correct normalization to make them a Dirac orthonormal collection. Okay, so we're going to kind of normalize even these continuous ones, even though they're technically not normalizable in the sense that their integral diverges from minus infinity to infinity. Okay, so that means this. Now, we don't just have to stick to k here. We might say, well, what if I wanted a Dirac orthonormal set with respect to p? So for example, I know p is h bar k. That's something you remember from modern physics, right? So if I wanted to write this expression as a function of p, I would have e to the I p over h, p prime over h bar, and here I would have a p over h bar, and here I would have a delta of p minus p prime all over h bar inside the delta function, which is not the same thing as delta of p minus p prime. So this collection, even though k and p are only one constant apart, they only differ by an h bar, this collection with these normalization constants out in front aren't Dirac orthonormal with respect to p, only with respect to k. That allows me to solve for the expansion coefficients as a function of k. What about if we want to parameterize those same set of functions by p, which is h bar k? Well, you can imagine the normalization constant is not too different. This is what we demand to be true. This is what it means to be a Dirac orthonormal collection with respect to parameter p. If we could also parameterize those free particle functions in terms of e. This is what it would mean to be a Dirac orthonormal collection in terms of e, where e is equal to h bar squared k squared over 2m for a free particle. What are the correct normalization constants? I sort of motivate this in the notes. I'm not going to talk about it here in class. It's just too much detail, but you don't have to know where it comes from. But if you want to look, it's there in the notes. The p is pretty easy to figure out. You just need an extra factor of h bar in that square root that we put for the Dirac orthonormal with respect to k ones. For the e, you do have to think harder. Notice here that for energy, all I've done is substitute what k is in terms of e there. That's easy, right? Just reparameterize it in terms of e. But the constant is different, and the constant actually depends on what energy you're talking about. So it's like a constant. It's not really a constant. It is a function of e, which is that normalization constant there, which makes it Dirac orthonormal. So that makes it nice that I can solve for the coefficients if I'm expanding as a function of any kind of thing, okay? Now, the last thing I wanted to mention is the interpretation of the expansion coefficients. We said if we expand psi of x0 this way, then the magnitude of Cn squared is the probability that an energy measurement yields the value En, magnitude of Cn squared. Here's what the corresponding things are for other expansions. Suppose V doesn't have a discrete energy spectrum, but has a continuous energy spectrum, and I write some normalizable state as a linear combination of different E states with coefficients A of E out there. Then, as long as this is a Dirac orthonormal collection, I've bothered to Dirac orthonormalize them. You know, I should say, you know, if these functions up here, in the case we're familiar with, are not normalized, then those expansion coefficients would change. And they wouldn't have the correct interpretation in terms of a probability. The sum of all the Cn squares wouldn't add up to 1 and all that, right? So these have to be normalized. Similarly, these have to be Dirac orthonormalized in order for A as a function of E to have a simple interpretation. The magnitude of those expansion coefficients is the probability density, the one that we couldn't figure out back in chapter 1. We said it exists. How are we going to get it? It's in chapter 3. So that is the probability density as a function of E. And similarly for momentum, and similarly for wave number, right? I could write any function. If this is a complete set, I can write any function as a linear combination of size, which are parameterized by p, right? P is just h bar k. And the expansion coefficients gives me the probability density as a function of p. And if I expand, if I really wanted to expand as a function of k, and I wanted the probability density as a function of wave number, we'd have it. So that's where we're that is the complete picture. It gets lost in chapter 3 in a discussion of things like Hermitian operators and lots of technicalities, but that's where we're heading to. I wanted to kind of just show all these analogies in one place before we go on to chapter 3, which is next. Any questions on that, given that we haven't really justified all of it there? Some of it's in the notes. Some of it, to Dirac orthonormalize, say, the continuous part of the spectrum for the finite square well would be a huge pain. And so nobody's going to bother write it down. What we need to know is that they could be Dirac orthonormalized. And I can write down a symbol psi k, which I can imagine could be Dirac orthonormalized, and we'll wishfully think that it is already, even though the formula is not so simple. Okay, let's then go on to chapter 3. And you're going to find that at the very beginning, we will come back and meet everything that's in Griffiths, but we are going to do things in a different order, some things in more depth than Griffiths does. So even though sections 1 and 2 are super short, I think it was like 3 pages long, I'm going to put a lot of stuff in there about vector spaces, linear operators, inner products, norms, and stuff that Griffiths doesn't spend much, if any, time talking about. Okay. Here is a voting question that we answered, quite some time ago. Right? When we make this expansion of some normalizable function as a linear combination of definite energy eigenfunctions, think of simple harmonic oscillator or something like that, or I guess infinite square well, since we're starting at 1 there. These collection of expansion coefficients contain the same information as this. And we're going to start to take that more and more literally. We've been biased, and you don't want to be accused of being biased anymore. You're biased if you really want to always stick to things that are wedded to x. Why not have expansion coefficients which are more associated with energies, or other expansion coefficients which are associated with momentum? Why should we stick to x so much? We should be comfortable having a description of the state of a particle that tells us more directly about what probabilities are as a function of energy, rather than probabilities as a function of x, or similarly for momentum. Okay? So let's talk about how we're going to think of these states as vectors. I don't know, do you talk about these psi's as vectors in modern physics? Maybe in Chem 162 or something you do. So when we're thinking of vectors, back in physics 210 or something like that, we don't often change bases, or when we think of a vector, we just stick to one coordinate system and you give its components in that one coordinate system. In quantum mechanics, it's absolutely crucial that we think about different collection of axes or different collections of basis vectors that we could use. So here's an example of a single vector, v. It points a little bit up and to the right, let's say, in the room. And I could write its components down with respect to the xy axes, which I've drawn as horizontal and vertical, or the x prime, y prime axes, which are tilted. And no surprise, the components are different, right? There is no sense in which one set of those components is more fundamentally truthful, or I should believe in them more, I should think of their fundamental than the other one, right? If you give me the primed components, that's just as good as getting the unprimed components there, okay? The important thing here is that there is one vector, but lots of different ways to represent it. If we give components, it could look very, very different in different coordinate systems, but there's only one vector we're talking about. It's going to be the same way in quantum mechanics. So only one vector, different components in different coordinate systems. In quantum mechanics, the one vector is going to represent the state of the system. And we're going to start to think of those psi's of x are kind of like components that we've been using. One set of components. We've been really biased so far. Okay, there are different ways of representing that particular vector in different bases. So I'm going to think of this psi as a function of x at some particular time, maybe t equals 0 at some time, as the components with respect to an x basis at that particular time. Right? When we think of vectors in 3 dimensions, we only have 3 components. Here, I'm going to try not to switch cameras, but maybe Luke and Zach can watch just in the mini screen. If I wanted to, be suggestive about the analogy between this, I might say I'm gonna if I have a vector v, and I want to put its components in some coordinate system, which has basis vectors x1 hat, x2 hat, x3 hat. One way to display that would be to say, okay, I'm going to make a graph. It's kind of excessive to make a graph of just 3 numbers, but here's how I'm going to do it. I'm going to say, here's 1. I'm going to plot the height of some function at 1, which is the component of this in the x1, x2, x3 basis. 2 might be down here. 3 could be here. I know that's excessive to make a graph of 3 single points. But what we're going to have now is something that looks more like this. Instead of just 3 points, we have an x here, and we have psi at some particular time. It doesn't have to be 0. It could just be any time you choose, right? The state of the system at a particular time. Somebody gives me a psi. Now, I know it's probably not real, but I don't want to draw a complex number, so let's imagine it happens to be real at this time. I've got a psi. Hopefully it's normalizable, right? It eventually goes to 0. I'm going to think of it as having lots of different components, a continuum of components. One for every x value. There's a psi at that value. That is like the component that I'm giving. It's a complex number at that particular psi value. So I've really got not just an infinite number of components, but a continuum of components. So that's the sense in which this is components in the x basis. What about the other bases? Well, here's our first expansion that we've done many, many times now. If we expand from 1 to infinity, maybe these are our infinite square well functions, or if we start at 0, they could be our harmonic oscillator, definite energy functions. These CNs, that's also, we said, if you specify this, you're specifying the CNs. And if you specify the CNs, you can reconstruct this. So the CNs are just as good. The CNs are the components with respect to the energy basis. If I were to write that in a suggestive way, I would say, rather than drawing psi here, I'm going to tell you what the CNs are. I've got 1 at n equals 1, 2, 3, 4, 5. I'm not plotting psi anymore. I'm plotting CN. Maybe this one's big. Hopefully they're getting smaller. Otherwise, it wouldn't be a normalizable state. They can be complex, of course. They don't have to be real numbers. But we're thinking of those as components. So components in a different basis. Okay. I'm losing contact with my fancy virtual pointer I've got here. Okay. That's for the discrete energy case. What about the continuous energy case? Well, again, I could expand the same way we did before. If we've got a continuum of energies, we do an integral instead of a sum. Those A's as a function of E's are going to be my components. If I want to think of it as components in front of a unit basis vectors, these better be Dirac orthonormalized. These better be normalized. Then I can interpret those as simple probabilities. So, just like we do in 3 dimensions, we're always going to choose a basis that's normalized. It's just making trouble for yourself if you choose one that's not normalized. So discrete cases, we're always going to normalize. Continuous cases, we'll always Dirac orthonormalize. So there's some components. We could expand this as a linear combination of definite momentum states. We already found out what those were inside the free particle discussion, that section of the free particle. Expansion coefficients there. These are supposed to be Dirac orthonormalized. And here's our components. So I could write A as a function of P, or I could write Px if we really wanted to emphasize the X momentum part of it. Then that would be another continuous function as a function of Px components. So lots of different ways of representing the same thing. There's one state, there's one vector. only a single vector represents the state. It's the components that are changing because we got lots of different bases. The same way we showed for that one in 2 dimensions. You could just twist the axes and get different bases. Now, what's new for us compared to physics 210 is we're not in 3 dimensions, infinite number of components, maybe even a continuous infinite number of components. We're talking about an infinite dimensional vector space, and we have to be much more careful when we're doing that. You get out of the land of doing linear algebra kind of stuff, and you get into analysis territory. Analysis means you have to worry about convergence of things. If you write down an infinite series, I have to worry about a lot of stuff. If I write down a finite series, I know if each term is finite, the series is going to be finite, right? You don't have to worry so much. But as soon as you start integrating or doing infinite series, lots of interesting stuff can happen. So we'll put a positive spin on it. You do have to be careful. Okay, so we're going to take did you ever use this notation in modern physics for a vector? That doesn't look familiar? Okay, so maybe not in chemistry either. So you're used to putting an arrow over the top, at least in physics 210, that's what we do. In quantum mechanics, a vector is going to be denoted in what's called the Dirac notation. It has a lot of advantages over this other one, so we're just going to get used to it. You'll see the advantages in this chapter. We put the symbol that denotes the vector inside a vertical line and an angle bracket like that. And the angle bracket always points to the right. We'll see the meaning and the utility of that later on. So that's just a different way of saying a vector. Now here our vector is in an infinite dimensional vector space a lot of the time. Although we'll see for spin and things like that, sometimes we can reduce it to a finite number of components. But most of the time we're talking about infinite dimensional vector space. That's a vector sitting in one. What about the basis vectors, right? You've been talking about x hat, y hat, z hat, or I hat, j hat, k hat in your intro courses. That doesn't generalize so well to infinite dimensions because I'm going to run out of symbols pretty soon, right? I've only got so big of an alphabet. It's much better if you've got a discrete or continuous set to denote them by number subscripts, right? So I might say E1, E2, E3. I'm going to denote the basis vectors in 3 dimensions. Instead of I hat, j hat, k hat, I'm going to write them in quantum mechanics something like this. Or if I, if I wanted each of those basis vectors to represent states, I might write them that way. But we want integers to represent them. Why? Well, this is fine in 3 dimensions, but it doesn't generalize to infinite dimensions. If I wanted to write this in quantum mechanics style, I would say, here's my vector v. It's 3.1 times this one, 2 times that one, minus this one. Hey, that's nice. I can write it in summation notation, nice and compactly, which we couldn't with the I hat, j hat, k hat notation, just because we don't have a nice index going from 1 to 3. So this is quantum mechanics style you see right here. And oh, we've already kind of been doing that, right? Except now I'm thinking of this as not the components of a vector, right, those psi n's, but some vector that represents, in this case, I'm putting the symbol en in there because this vector is supposed to represent a state of definite energy. Anytime I have a vector, it's a state. I'm putting the symbol E in there to remind myself that it is a state of definite energy. And, if we're in the, boy, I'm really losing control with this thing. If we're in the harmonic oscillator, this would start from 0 to infinity. And this, would be a vector that has components in the x basis that would be our psi n's. Right? If I've got a continuum of different basis vectors, like for the free particle, right, we had states of definite wave number, e to the I k x. We'll throw in the 1 over root 2 pi in there to make them Dirac orthonormalized expansion coefficients. Yes, this vector can be written as a linear combination of the states of definite wave number, 1 over root 2 pi e to the I k x. There's nothing really new going on here, but it is a little bit unsettling just because the notation all of a sudden has become a little bit more abstract. What we thought were the actual states before were actually just biased components. Yes, Juan.
I'm confused about the dimension of the vectors. So, for example, like the second R, the first R, so psi is equal to the sum of the time En, right? So, what is the dimension of the vector En?
Well, so vectors themselves, usually we don't say have dimensions, but the vector space they're in has a dimension. So it's a vector sitting in an infinite dimensional vector space. So I've got an infinite number of these basis vectors. Right, so if I say I've got a vector, if I say here, I'm going to draw a vector, what dimension is this vector? You might ask, well, do you mean it's stuck in the board? Like just sitting at looking at a vector, maybe I mean, oh, it's stuck in this one dimension. It could be a one-dimensional vector, right? Or a vector in a one-dimensional vector. Or maybe I mean it's part of a collection in the board. Or maybe I mean it could come out in 3 dimensions, but it's not. So vectors themselves don't have dimensionality, but the spaces they sit in do. And in this case, each of these vectors are supposed to be residents. Gosh, I'm having a tough time with this. My problem is I got 2 things going on here. Oh, I did it again. Maybe if I turn this off and sort of reset it, it's like flying all over the place. But I do like this thing. They haven't quite progressed to the point. Uh-oh. Now I've done it. These virtual pointers have not progressed to the point where they're reliable. Okay, let me try advancing. Let me try displaying. Okay, I'm back now. And I seem to have more control. I can't gesture too wildly, I guess, with this. Yeah, so these are vectors in infinite dimensional vector space. You know, just like the basis vectors in 3 dimensions are denizens of 3-dimensional vector spaces, and so is an arbitrary vector, which can be written as a linear combination of them. Here, all of these are supposed to be elements of an infinite dimension of vector space. Okay, other questions? We're going to start building up structure. So we're going to do math for a little while. We're thinking of states, quantum states, because we know some examples, but we're going to do some math. The second from the bottom. No, the c squared would be, magnitude of c squared would be a probability, but these are just expansion coefficients, just like this isn't squared either, right? When we write an arbitrary, well, let's go back to this previous slide here. I'm now clicking very slowly because I'm paranoid, right? This is our usual way of expanding, right? It's just expansion coefficients in front of states of definite energy. But now I'm going to think, oh, well, wait a minute. Those weren't the abstract vector states. They were sort of a representation of the vector in terms of some very biased coefficients, right? I was writing them as functions of x because I really like x the first time. I mean, you've got to stick to something the first time you see quantum mechanics. But as soon as I expand in terms of these, I might as well say, hey, let me just think in terms of the CNs now. The CNs represent the same state as the psi of x0. So yes, that shouldn't be squared there. The associated probability would be magnitude of Cn squared. Okay, so what is a vector space? You've thought about vector spaces in a few dimensions before. Well, we need to be careful to define it. It's a collection of vectors, things. You can just think, well, I don't know what a vector is. It's a collection of things that can be added and multiplied. In other words, we can take linear combinations of them. And importantly, they have to still remain in the same collection. So you're going to specify a big collection. And the claim is if you take any linear combination of those things in the collection, it should still lie in the collection, right? If I take 8 vectors in 3-dimensional real vector space, right? We're living in a 3-dimensional vector space. Grab 16 vectors and put arbitrary complex coefficients out in front of them, or maybe if we're thinking of a real vector space, take a real linear combination of them, you're going to get some other vector in the vector space. It's still going to lie in the same vector space. It might be really big, but it should still be, in the same vector space. Okay, it's got to satisfy, mathematicians who study these things have a collection of axioms. You don't need to memorize these. I just want to emphasize a couple of things. This for us is the most important one, because we're going to find it's easy to run afoul of this. The set has to be closed under finite linear combinations. That means if you take any n vectors, I don't care how big n is, but it doesn't have to be infinite, right? It doesn't have to satisfy that to be a vector space. Whoa, I did something again. Let's go back. These two, my pad was talking to this thing and somehow going crazy. So They got to be closed under finite linear combinations. Now, in quantum mechanics and infinite dimensional vector spaces, we're going to take infinite linear combinations all the time. We have to be very careful with those. But here we only require that if you take a finite linear combination of elements, you still get back inside the same space. There's the usual axioms. None of these things should look surprising to you if you think about ordinary vectors. You scalar multiply any vector by 0, you get the 0 vector. You scalar multiply any vector by 1, you get that same vector back. Bold here means a vector. That was just whoever I stole this from was using that notation, so I'm not using quantum notation. The usual distributive kind of stuff. So nothing surprising here. It's the closure I really wanted to impress upon you, because we're gonna see cases, or we'll do a worksheet in just a second, where you'll see it's easy to not be closed. You think you have a vector space and you actually don't. Okay, so usually when you say, well, what vector space are you talking about? Someone comes up with a particular basis. So if I want to say, I'm talking about a 3-dimensional vector space, and you say, what one? I say, okay, the x hat direction is this way, and the y hat direction is this way, and the z hat direction is this way, and we're going to take linear combinations of it. It's just very useful to say, instead of saying I'm thinking of an abstract space, I just give you 3 vectors, and I say you can take any linear combination of those you want, and that's our vector space, right? Even though that's being a little bit biased towards these vectors that you specify, it's a convenient way. You got to give someone some information to say what vector space you're talking about. Okay, so the usual one we would think of back in physics 210 is, it's a real vector space, and what that means is, for those basis vectors, the things you're taking as the scalars and the linear combinations are usually real numbers, right? We don't allow complex components if we're trying to specify positions or momenta in classical mechanics. But you could, and so are you guys familiar with this notation for the real numbers and the complex numbers, that kind of bold symbol? So you could have a 3-dimensional complex vector space where you could have, 1x1 hat plus 2 minus I times x2 hat, and so on, right? A complex linear combination. So it's important to specify when you're defining a vector space, what are the scalars that are allowed? Am I sticking to real numbers, or am I allowed to use any complex number I want in linear combinations? Okay. In quantum mechanics, what is our space we're talking about? Well, again, I have to specify it somehow. We're used to thinking of functions of x. So let's define the vector space using functions of x, but then we'll be able to recast states in other bases. So in quantum mechanics, we could say our vector space is the set of all square integrable complex functions. That's our psi of x0, such that the integral from minus infinity to infinity of psi star psi is some finite number, right? Can't be infinite, can't be divergent integral in any particular way. It's got to be finite. So we call those square integral functions, in that the integral of the magnitude squared of the function is finite. Oh, here, I've got it right down here. Set of all functions of x, complex functions of x, such that this is finite. Finite means it converges, and it converges to a finite complex. Well, I guess it would be a real number. This has got to be real. You can prove that to yourself. F star F is a real number. Okay, there's a notation for this. I can't remember if this is in Griffiths or not, but if you go on in math and functional analysis, this is very common. They call it capital L2, functions of the real number line. So that this is their domain right here, from minus infinity to infinity. And the 2 is supposed to remind you of square integral functions rather than 4th power integral. Mathematicians think of all kinds of stuff. And, well, I don't know what the capital L is supposed to represent. Who knows? Maybe it's Lebesgue integration or something like that. But square integral, that's what the 2 is, okay? It's an infinite dimensional vector space. Its elements, normally we'll think of its elements as functions of x, but you could also think of each function of x is just a biased representation of an abstract vector in that space. I don't know how to picture the abstract vector of an infinite dimensional vector space, but psi as a function of x is just one way of sort of projecting out components. The CNs are another way, and the phi of p's are yet a third way. Okay. Again, I'm just emphasizing here, there's nothing fundamentally special or preferable about the basis. So the x basis that I'm using to define my functions, or in the 3D example, we used a particular basis there. It's really difficult to say anything about what you mean if you don't start with some basis and say, hey, we're building things out of this. Now I can consider other bases when I've defined one set of basis vectors, and we can talk about switching to other ones. So we are going to start usually by thinking of functions of x. It's just that we're going to project it out, the information out different ways. Oh, and I forgot I was going to hand out, this is from the notes, this page. It's just got a little handwritten summary of a lot of properties, and so I'm going to touch base with it as we go along. So some key terms that we're going to be defining. For those of you watching the video offline, we are going to, you can get this from the notes that are on the website. It's in the middle of the notes. Right, so a vector space, we define what that means. In quantum mechanics, the scalars we're concerned with are always going to be complex numbers, right? We're used to real numbers, but now, in quantum, complex numbers are all over the place. And the key thing is it's got to be closed under taking finite linear combinations. Important special cases are capital L2. This is the space of all square integrable functions of a real variable, right? In quantum mechanics in one dimension, we're still taking complex functions of the real number line, right? That's the domain. Here's another sort of, it seems like it's a different vector space, but it's just a different way of specifying the same thing. Little L2, here I usually write it with a script L. It's hard to tell because, if I don't do a script L, it looks like the number 1. Little L2 is the set of all square summable sequences. Notice that if I gave you the CNs in that expansion, I would have told you what state we're in, right? What has to be true of the CNs? Well, it's got to be true if I take the magnitude squared of C1, add it to magnitude squared of C2, all the way up to infinity. That better be a finite number. Hopefully it adds up to 1. That means we're talking about an expansion in a normalized set of states. But it's got to be square summable. Otherwise, we would say we're not in a normalized state. Not only is it not normalized, it's not normalizable if it doesn't, the sum of the squares of those CNs don't add up to something finite. So I could give you the CNs, then I'm sort of specifying it this way. I could give you the size as a function of x in this way. And of course, we could have finite dimensional vector spaces. Okay, so let's start doing some worksheets. We're going to practice with this stuff. I know it's all very new feeling. If you're watching the video, I sent an email attaching these. We're doing the first of the vector space worksheets. So here I am describing in words some collection. Here they're all functions, I think, functions of x with different properties. And you're supposed to decide. When we say a vector space over the complex numbers, that just means the scalars are the complex numbers. Over the real numbers means the scalars are the real numbers there. So A is saying the set of all functions with real outputs at every x. So they're functions of real numbers that give outputs that are real numbers, like sine of x or e to the x or something like that. Is that a vector space over the complex numbers? Is that a vector space over the real numbers? If I take arbitrary complex linear combinations of them, do I get something in the same collection that I described to begin with back or not? Do we go outside that collection? So try to answer these 5 as they're stated, and we can look at the differences. Should we just talk about the first one together to make sure everybody's on the same page? The set of all functions with real outputs. That's my, I'm putting in scare quotes, vector space. Is it really a vector space? The set of all real functions of a real variable. If my scalars are the collection of complex numbers, if I take a complex linear combination of two real functions of x, will I get a real function of x? No. Right? I can put an I in front of something and already it's not, I mean, that's a trivial kind of linear combination of just one thing, right? Sine of x plus I cosine of x, right? That's not a real function anymore. It's not in the original collection, so it's not over the complex numbers. Over the real numbers, yes. If I take a real number times a real function plus another real number times another real function, I'm going to get some other real function back. So that is a vector space in that case. That's the kind of reasoning we're supposed to be doing here. All right, it's looking like you guys have answered them all. So let's just talk through them. What do you say about B, Jack? The set of all normalized functions, integral of the square of the function is equal to 1 with complex linear combinations allowed. Is that a vector space or not? Yeah, I would say no too, because even if I put a 2 in front of it, I've messed it up, right? That's the very trivial linear combination of one thing is just scalar multiplying, right? Okay, good. Will, what about the set of all functions that asymptotically go to 5 as you go out on the positive x-axis and also on the negative x-axis? That's how I defined it. So in this case, I didn't say whether the functions were real or complex. Maybe I should have been more definite, but let's say they're real functions that asymptotically approach 5 and the scalars are the real numbers. What do you say about that? Is it possible for me to take a function that asymptotically goes to 5 on the two ends, right? Maybe it's wiggling around in the middle, but it asymptotically goes to a height of 5 and take another one of those, it's wiggling in a different way, and take some linear combination of them and end up with something that doesn't go to asymptotically to 5? Yeah, I mean, in fact, if I just added those two functions, the sum would asymptotically go to 10, and that's one easy way to do a linear combination. So that's not a vector space. You can see you have to be very careful. All right, Huang, what about D? The only difference is it asymptotically goes to 0, and we're taking complex numbers. I didn't say what kind of functions. Let's say they're complex functions in this case, but they asymptotically go to 0. Yes, because if I take any complex function that asymptotically gets closer and closer to the x-axis, right, it's going to 0, and I multiply it by any complex number, that resulting function is still going to go to 0. So if I take a scalar multiple of one of those and a scalar multiple of another one, those two are going to go to 0. When I add them, they'll also go to 0. as you go out there. So that is a vector space. Set of all continuous functions over the complex numbers. What do you guys say about that? If I take, just say 2, we in generally have to take a finite number, but if it breaks with 10, it's going to break with 2 at some point because you can just add them, take linear combinations successively. So is it possible to take a linear combination of 2 continuous functions and end up with a discontinuous function? Yeah, I don't think so. You can think about limits and stuff like that, right? If I think about any point and I say, the limit as x goes for my first function, as x goes to 2 from the right approaches the number 3, and also as I approach from the left, somehow it approaches the number 3. That's a continuous function, right? And my second function, it approaches the number 7, right, from both sides. I don't really care if it has a divot in it like that. We're just concerned about continuity. So this one goes to a height of 7. Then if I take, the simple linear combination of the sum of those, it's going to go from both sides to 10. Doesn't matter if I put other numbers in front of it, right? It's still going to be continuous. It takes a little bit of thought and creativity to think about those. And more questions on those. We're not going to be making up too many random vector spaces. For us, we're mostly going to be concerned with square integrable functions. That's a vector space. And square summable sequences. That's a different way of describing the same vector space. All right, let's go back on the screen share. Okay. And see what's next. Okay. Inner product means the same thing as a dot product before, right? You're used to the dot product in 3 dimensions or something. We're going to define a dot product or inner product is the more highbrow way of saying the same thing on our vector space. So the idea is if I've got a vector, abstract vector, now I'm thinking, this is the abstract notation, W and another one V, and I want to take their inner product. If this is a complex vector space, there's actually, we're used to thinking in real vector spaces that x, the W dot, V dot W is the same thing as W dot V. That's a function of working with the real numbers. In this case, there are 2 ways to take the inner product or dot product between these 2. One of them we denote like this, and one of them we denote like this. It depends which one you put on the one side or the other, okay? Means the same as the dot product. And again, there are axioms. We're not going to spend too much time on the axioms, but it is a little bit less familiar to us. I mean, I guess, if you have the sum of 2 vectors, dot product with another vector, you can distribute over the sum and get a sum of 2 individual dot product. I mean, that kind of stuff we're familiar with. This we're not familiar with, the conjugate symmetry, because in real vector spaces, the dot product or the inner product is symmetric. In complex vector spaces, we're going to see why this has to be true. The inner product of x with y, vector x with vector y, is the complex conjugate of them taking the inner product in the other direction. So you get the complex conjugate when you switch the order you take it. We'll think about that with a voting question in just a second. The other thing that's important is this positive definiteness case down here. The inner product of a vector with itself has always got to be non-negative. That represents kind of the square of the length of the vector. We'll define that a little bit later, right? Well, we usually require that the inner product of a vector with itself should be non-negative and only equal to 0 if the vector itself is 0. In other words, the squared length of the only vector that has squared length 0 is the 0 vector. That the existence of the 0 vector was one of the axioms of the vector space. Every vector space got to have a 0 vector. Okay. Here's a voting question about a 2-dimensional vector space, C2. So Vectors in 2 dimensions, right? There are only 2 basis vectors, but we're talking about complex linear combinations because it's more similar to quantum mechanics. The components, so here's a vector. Let's say its components with respect to a particular basis is V1, V2. We're kind of used to that notation, right? Those tell me the components, but they're complex numbers there. If we want the inner product of this vector with itself to be positive and non-zero, and only, sorry, positive for non-zero V and only 0 for the 0 vector, that's that positive definiteness condition. How are we going to have to write a formula down for the inner product of A with B? You're kind of thinking analogously with if somebody gives me the components of vector V in a real vector space and vector W, I know how to calculate the inner product. It's V1 W1 plus V2 W2. Now we got to think. Now those components could be complex, and I've got to satisfy that last axiom about non-negativity and 0 only for the 0 vector. This takes a little bit of thought. Think about those options there of what do we have to make our formula into to make it work for complex components, complex vector spaces. I'm just going to flip back here because we're saying if this is going to be true, then the inner product of a vector with itself has got to be a real positive real number, and it can only be 0, non-positive, when the vector is the 0 vector. So it's got to end up being real, and it can only be 0 if we have the 0 vector. Do you guys have a vote? It looks like you're all turned to the same thing. I don't know if you're voting that, but everybody has a B or a 2. And I agree. I mean, it takes some thought, you know. This one, can anybody give me an argument why A is out? That's the formula for a real vector space. It better reduce to that for real numbers, and B certainly does reduce to A when you have only real components, right? The stars don't do anything. Why is A not going to work for complex vector spaces? Yeah, I mean, I can get all sorts of things. I can get negative numbers. I can get complex. This could be a complex number right here, right? I might have components. A might have components I, 1 and I, and B might have components 1 and 1. And then this combination is going to be 1 plus I. Well, that's not a non-negative real number. The inner product is, we're still going to require the same kind of interpretation. The inner product is the degree of overlap expressed as a positive real number, or it could be 0 if you're taking the inner product of a vector with itself. And it's the 0 vector. What about this one? That one, I've got to think for a second. This certainly makes it into a real number. It certainly makes it into a non-negative real number. So why wouldn't that one work? It actually does violate, if I remember correctly, I'll have to think up an example, that last axiom, which says that the inner product of a vector with itself can only be 0 if the vector itself is 0. Can I think of any vector and that has complex components where I'm taking the inner product with itself? That's like saying, I've only got one vector A, and I'm going to take A. Let's suppose A has components A1, A2, and they're complex numbers, right? When I calculate the inner product with itself, according to C, I'm going to get the magnitude of A1 times A1, right? Plus A2 times A2, where those numbers can be complex. Can I ever make this combination 0 even though the components themselves aren't 0? Yeah, I could make A1 1 and A2 I, right? If A1 is 1 and A2 is I, remember it's a complex vector space, then I get 1 squared plus I squared, which is 0, but I start out with something that's not the 0 vector. The 0 vector always has all 0 components in all bases. So this is going to sort of generalize to a lot of stuff in quantum mechanics. That's why we often see stars next when we multiply two functions together. One of them is always starred. We're kind of doing an inner product, we just weren't putting it in that notation. Okay, so B is the one there. And in fact, here's a proof that it's always real. I forgot I put this in here, right? Let's say the components of this vector can be an arbitrary complex number. So I'm thinking A, B, C, and D, lowercase, are all real numbers. So here's an arbitrary complex number. Here's another one. If I calculate the inner product of it with itself, according to, say, here I'm doing the example of A, well, that's not a real number. But if I do it according to the correct one, B, I get an A minus BI times A plus BI is A squared plus B squared, which is definitely a real number. Remember, if little a and little b are real, they could be negative, but the square of them is definitely a real number. And in fact, it's going to be a non-negative real number. And you can check that it's only going to be 0 if I take the inner product of a vector with itself, if A, B, and C and D are all 0, which is to say it's the 0 vector. Okay, too much of a good thing there. But that we're got to get familiar with this formula, thinking of complex vectors for the inner product. Okay, so if, just writing out things in terms of components, if I write out in a 3-dimensional complex vector space, here is a vector. It can be written as a linear combination of the 3 basis vectors that I'm imagining. So can V, right? W has components, V has components. If I take the inner product, whichever one's on the left, it gets the stars. That's just convention. The one on the right doesn't get the stars, okay? And we can write it nice and compactly because we got our integer indices. Okay, if infinite dimensional, for example, discrete set of basis vectors, right? These are sort of like our definite energy states written as abstract vectors. Here are the expansion coefficients. I'm thinking of, here's one psi of x0, but I'm now conceiving it as an abstract vector. Here's another psi of x0, psi prime of x0 or something like that, right? It's got a different expansion coefficients. If I take the inner product between them, I get an infinite series there of 1 star times another, right? C1 star times D1 plus C2 star times D2. That's how we're going to calculate inner products. Same thing with even continuous basis representations, right? We're imagining here our free particle definite energy eigenstates or definite K eigenstates. They form a continuum. We can write an arbitrary vector as a linear combination of those. These are the components. Here's another vector. It's got different components. If we want to take the inner product, we got to multiply the similar component index, put a star in front of the appropriate one, and add them all up. When you have a continuum of things and you add them all up, that means integration, not summation. If you got a discrete collection, you add them all up by summing. If you've got a continuous collection, you integrate. Okay, let's pause for a minute and take a break because we're about an hour in. I'll drink a bunch of coffee, which is probably not a good thing, but so what? Yes. Lots of math stuff. I mean, you hopefully, if you're in quantum mechanics, you love math because there's a lot of new math and it's very exciting to learn, you know, connections with analysis that you don't learn in calculus, and infinite dimensional vector spaces and infinite matrices will be multiplying, even continuous matrices that have a continuum of elements in them. So if you've taken linear algebra, we're going to be going way past what you do in linear algebra here.
Really fun. And you've fallen just far enough behind where, like, the last lesson normally does is it shows that actually you can apply these principles to arbitrary things as long as you define the basis for vector space. So we didn't do that with this part. So
Yeah.
I just got left with the raw linear algebra. Wait, this isn't just for the sake of itself.
Doctor Who? Oh, okay. I remember when I arrived at graduate school, I'm not sure how many other schools do this, but they gave us a diagnostic exam, you know, well before classes started, to just see where you were kind of at in terms of generic, pretty easy undergrad stuff, but some of it was mathematical techniques, and one of them was to find the eigenvalues and eigenvectors of a 3x3 matrix. And, you know, everybody probably had seen it before, but I remember there were a lot of people who were like, oh, I didn't remember how to do that. But it's important for quantum mechanics, for sure. In fact, we will be finding eigenvalue. You already know eigenvector, eigenvalue equations are important. We're going to be finding even for 3 dimensions, but also in infinite dimensions.
So I'm writing code that will make an n-dimensional matrix as opposed to a 2-dimensional matrix. So we can't display that. It comes up more often than
Oh, like an array. Yeah. I mean, certain coding languages have, I mean, MATLAB has that natively in it, right? And I'm not sure, is there a limit on the number of dimensions you can have in MATLAB? Do you know? Or Python?
So I do know that C only has vectors, or arrays, I should say.
Every array is inherently one-dimensional, and you've got to do the reconfiguring in your own manipulation of it. Yeah. That is one thing that's nice about MATLAB, is that a lot of, yes, okay, of course you could all do it on your own as a linear list of things that I'm thinking of as a 10-dimensional array. But God, I gotta be on my game, and it's nice to have that done in just somebody else has low-level coded it. You know, they coded it in C. It's reasonably fast. I'm probably not going to beat their algorithm coding it myself anyways. So why not just have it in a collection of routines, you know? I remember when I was a grad student, we were still using Fortran quite a bit, and Fortran had a limit of 7-dimensional arrays, if I remember correctly. And there were often times where we wanted to go bigger, and then you would have to start thinking of, okay, it's a stack of these and then a stack of those stacks. And I've got to figure out how to organize everything so that it works out the way it's supposed to. All right, other questions? We're probably up to another worksheet problem, I bet, here. Oh, okay, one more definition. So we got an inner product now. You got to have the stars. There are 2 ways to take an inner product. What does the term orthogonal mean? Well, the same thing as before. If the inner product or dot product between 2 vectors is 0, we call them orthogonal to each other. You know, it's hard to imagine in infinite dimensions what perpendicular means, but it's supposed to be the generalization of perpendicular. Okay, So here again on the sheet, just, just some quick things. Here are the key properties that have to be true of an inner product, right? Are the ones that you wouldn't consider obvious just from your knowledge coming into the course. Here's the definition of an inner product of two sets of components on capital L2. On little L2, you have an infinite number of components, but you just multiply them element by element, put a star in one of them, and add them all up. We still have to worry about convergence of things like this, but we'll talk about that later on. And the definition of orthogonal. So let's look at the second worksheet problem. What's the inner product between the two given functions there? I can hardly read my version. It's been scanned in. E to the minus absolute value of x and e to the minus 2 absolute value of x. I guess it's worth mentioning in B, I'm asking for a non-zero function. If one of your vectors is 0, you wouldn't call it orthogonal to anything else. When you're saying two vectors are orthogonal, both of them have to be non-zero vectors. Otherwise, people will look at you funny. Oh, God, I got it right over here. All right. Looking at you two here, it looks like you're through this particular problem anyway. So let's talk about the first part, part A. Here are two functions, which I'm really thinking of as the x basis components of vectors. Here we're using the abstract notation kind of in terms of the vector f. But if I take the inner product between those two, it's by its very definition, when we've got functions like this, these certainly are square integral functions. We're going to use the usual definition on little L2. This means the integral from minus infinity to infinity. The g gets the star because it's on the left. The f gets no star because it's on the right. And we just calculate the integral of the product. And it works out, I've of course designed it so it works out nicely. This is equal to, let's plug in the things, g starred, the 4i turns into a minus 4i, and I'm going to factor it outside of the integral because it doesn't depend on x. Nothing happens when I star this, so I get an e to the minus 2x times e to the minus x is e to the minus 3 absolute value of x. And then how do I integrate that? Yeah, I mean, it's got the same area under this curve to the left and the right, so we could just put an extra factor of 2 out here and only integrate from 0 to infinity. And in 0 to infinity, absolute value of x is just plain old x, and now I'm back to calculus, right? So this is e to the minus 3x over minus 3. That's the antiderivative of that function evaluated between 0 and infinity. Upper limit gives 0. Lower limit gives e to the 0, which is 1 over minus 3 is, I guess that's a plus 1/3 because the lower limit comes with a minus sign and I already had a minus sign there. So I believe this whole integral is positive 1/3, right? Did we get that right? And therefore, this is equal to minus 8i over 3. Yes, that's what I have in my solution too, so I didn't mess anything up. Inner products, they can be complex. It's just the inner product of a vector with itself has to be a non-negative real number, but inner products in general will be complex numbers. And in B, this is supposed to be just a recognition problem. What is a function without thinking too hard that is orthogonal? Non-zero function that's orthogonal to this thing, which hopefully looks very familiar to you now. Come on, where's my, oh, there we go. Hopefully that looks familiar to you. It looks like a definite energy eigenstate for the infinite square well, where what we usually call A is 7, right? I've got n pi x over A. We're talking about n equals 3. And you can even do the calculus. It's a little bit of a pain, but you got to think about integrating a product of different sine functions. If I take any of the other definite energy eigenstates, like sine of 4 pi x over 7, with the same, it's that value in between 0 and 7 and 0 everywhere else, those two functions are definitely going to be orthogonal. And in fact, you can use your calculus 2 techniques if you go back and dig into it to prove that the integral from 0 to 7 of sine of n pi x over 7 and sine of m pi x over 7 dx is equal to 0 unless n is equal to m. You got to think about it. You got to do when your trig identities and put the signs together and all that kind of stuff. But that's how you would prove that they're orthogonal. But we have generally found out that the different energy eigenstates corresponding to different eigenvalues are orthogonal. And in this case, we can actually prove it pretty easily with elementary calculus and trigonometry techniques. All right. Let's talk about a third thing, the length of a vector. The math term for that is the norm, right? That's what we talk about normalization. So the norm is the length. It's the same thing as the magnitude, the normalization. And we're going to define it. And in math, it's almost always, you can vary from this, but most common it's defined in terms of the inner product. So the length of a vector, you could either write that as this notation, put the double bars, that which means how long is the vector, or what it's defined to be in terms of the inner product usually is the square root of the inner product of the vector with itself. In other words, inner product of a vector with itself is the squared length of the vector. So think in terms of our function, what is the norm of, if I think of a vector, well, what I do is take the inner product with itself, and then I should make the square root of it. I'm not sure why I didn't take the square. This better be a finite number if we're talking about square integral functions. It would look like this, or if we're representing our vector by a sequence and so on. Okay, and we say a vector is normalized if its inner product is 1, which is to say the square root of the inner product is 1, right? It's normalized if its length is 1. Okay, now we can define something about a whole collection of vectors. We can say a collection of vectors is orthonormal, a discrete collection of vectors, if they're normalized and they're mutually orthogonal to each other. So even if I'm in an infinite dimensional vector space, I could give you a collection of 5 vectors. And I could say, these 5 vectors are orthonormal. They're normalized and they're mutually orthogonal. They don't span the whole space, as you might say in linear algebra, but they are an orthonormal collection. And now we can define Dirac orthonormal, at least with respect to a parameter like k or something like that, means that if you take any different parameter, k and k prime, k not equal to k prime, then their inner product is 0. If you do k equal to k prime, the inner product is actually equal to infinity. But if it's exactly infinite in a way that makes this a Dirac delta function, we call it Dirac orthonormalized. So I think, yes. So now we're ready to do a lot of worksheet problems. Okay, so orthonormal collection of vectors. Anything else I need to say in here? No, I think we've talked about all those things. So let's look at the last one on the first worksheet, worksheet problem 3. And then I'm going to hand out a second worksheet. And again, if you're watching this video offline, I emailed that one as well. We're just ready in these problems 1 to 6 with practice with a lot of these sort of concepts. I guess I didn't give you the Gaussian. I should have put the Gaussian integrals that you need for 3a, right? Yeah, well, from 0 to infinity. But they're not on. I mean, it just seems like I would have put it on here, but it's not on there. They are on the second one. So there you go. They were meant to be passed out together, apparently. Remember, little L2 is the set of all square summable sequences. So you should be naming in one a pair of sequences, each one of which is square summable. The magnitude squared summed from, you could take your index starting at 0 or 1, it doesn't really matter to me, to infinity should be something that is finite. It converges and it it's not infinite and it's not just purely divergent without going to infinity. It is a finite number. Help me out with 1A. I just want to make sure everybody's okay with that one. How do I write down a sequence? I've got to write down an infinite progression of numbers such that I'm sure it's square summable. One way to do that is to make every element of the sequence go to 0 after a while, right? You can say, oh, okay, it's going to be 5, 4, 3, 0, 0, 0, 0, 0, 0 forever, right? Of course, that's square summable. But what if I wanted some truly things where every element is non-zero? What are some examples that are easy to produce? 1 over n, yeah, 1 over n. So if I take the magnitude squared of that, right? So we would say, you might say starting at n equals 1. So our sequence would be 1, 1/2, 1/3, 1/4, and so on. We get the idea. That's an element of little L2, right? That's inside little L2. Why is it inside little L2? Because if I take the square of this, I get the sum from n equals 1 to infinity of 1 over n squared, which is a finite p-series. That is a p-series that converges. Got to remember your facts about p-series. We could also do something like a geometric series, right? 1, 1/2, 1/2 squared, 1/2 cubed, and so on. That's a convergent geometric series. That's like x equals 1/2. If I sum from 0 to infinity of 1/2 to the n, I get 1 over 1 minus x. That's that one convenient formula you learned in series. Are you guys done with 1 to 6? I just want to make sure you're not waiting on me. Yeah, you're supposed to be doing on the second worksheet 1 through 6 as well. It's just a lot, I'm just throwing a smattering of things at you and making you use the definitions. As you can tell by the space, there's not supposed to be a lot of calculation involved with most of these. It's just making sure when you see the definitions, examples to come up with that you can think of that are convenient. Because if you can't come up with one non-trivial example, well, that's going to be a problem with thinking about what it means. I feel somewhat compelled to give you guys more worksheets, especially if we have 2-hour sessions. It's just too much to talk the whole time without taking a break and thinking and writing yourself. All right, how are you guys doing? You getting close? You done, Jack? Looks like you've got something all the way through the end. Let's talk about them together. Let me unshare the screen here. Whoops, stop share. There we go. So there are lots of examples for A. One, like I said, one easy way is just to put a bunch of zeros at the end of the series. That's certainly square summable, but then we could be trickier and, use something like a geometric series. I guess this is going to be, when I take the square sum of this, I'm going to get 1/4 to the n, right? Something like that. So they're both square summable sequences. If I add them, well, yeah, I mean, something weird happens in the second position, but who cares? It's still a sequence, still square summable. When I add them, scalar multiply the second one by 2i. I won't bother to do that. You just put a 2i everywhere up in the numerator. Okay. 2. Give 2 examples of elements of capital L2. That means square integrable functions. Your second example should be non-zero everywhere. So I said in 2, my examples were, well, I took one kind of cheat function. I said, oh, I'm going to make it only 1 between 0 and 1 and 0 everywhere else. That's sort of like the same cheat I did up there, right? There's no problem integrating it from -infinity to infinity because its value, its squared value is 1 only on like a little region. My second one's supposed to be non-zero everywhere. The obvious one, I guess I took, was the Gaussian function. We all know if we take the square of that, we get another Gaussian. It's perfectly finite integrable. E to the -2x squared has a finite integral from -infinity to infinity. Any questions about adding them or scalar multiplying them? I'm just forcing you to try those things. So it doesn't, just sometimes people get the wrong idea about it. So stop me and tell me to write it down if you want me to do that, any of those B's and C's there. Give example 3 of elements of C3. Your second, no, C3. So I said my elements are going to be V is 1, 2, 3. Real numbers are complex numbers, so I make my life easy. W I took as 4, 5, 6. Again, usually, I guess I should be careful here. Some people are very picky to say, hey, this is an abstract vector. These are the components of that vector in a different basis, and they're not the same thing, right? There's only one vector here. It has lots of different components in different bases. I shouldn't really put an equal sign between it, although people do it all the time. We all know what we mean. This abstract vector is going to be represented by its components in a certain basis. But here I'm putting a colon there as a nod to people who are very finicky about not saying equal if they're not exactly the same thing in all respect. So an abstract vector can't be a collection of components technically. And if I add them and scalar multiply them, nothing interesting happens. Okay, any questions on that one? Producing the examples is the most interesting thing. Here I've got 2 kind of geometric sequences which are square summable. If I take the inner product between the 2 in 4, I got to put a star on the first one times the second one. It looks like they're all real, so the star doesn't do anything. So if I do W inner product with V, that is going to be a sum. My index goes from 0 to infinity here of W gets starred, but there's no i's in there. Oh, there is an I over 3 to the n. So I get it minus I over 3 to the n times 1 over 2 to the n. And that's easy enough to do. I can factor the minus I out in front. Sum from 0 to infinity of 1 over 6 to the n. And that's one of those geometric series, which is the 1 over 1 minus x. To use the 1 over 1 minus x, it's got to go from 0 to infinity. You can't start from 1 to infinity. I sort of had a little, you had to you lost a point, I think, on the exam if you use that geometric series formula in the wrong way, but no big deal. Sum from 0 to infinity of this is 1/1 minus 1/6 minus I times 1/1 minus the thing that's being raised to the nth power here, and that's a 1/6 to the end. That's 5/6. 1/5/6 is 6/5. So this is equal to minus 6I/5, I believe. Yeah, that's what I have in my solution. Nothing exciting about it, but the thrill is realizing, oh, okay, I can write down some of these things and actually calculate some things sometimes if they're convenient. Calculate the norm of V. So I have to, that's going to be the norm of V is going to be the square root of the inner product of V with itself. V was the one that had the 1/2 to the n. So that's going to be the sum from 0 to infinity of 1/4 to the n, which is a 1/1 minus 1/4. 1 minus 1/4 is 3/4. 1 over that is 4/3. So I believe this is the square root of 4/3. That's what my solution says too. So these are supposed to be just easy. I like these creative problems, right? I mean, you can actually, there's lots of difficult series out there, right? Any generic series you write down, you probably can't sum, but we have lots that we can play around with. Here are two functions in capital L2 in 5. E to the minus x squared and x cubed e to the minus x squared. And we're supposed to calculate the inner product between them, which is something easy. It's 0 because it's an odd function, symmetric limits, right? I get x cubed times e to the minus 2x squared. E to the minus 2x squared is even. X cubed is odd. So the product of an even and odd function is, hopefully you reasoned about that kind of stuff back in calculus, even and odd functions. Product of even and odd is odd. If you integrate an odd function between symmetric limits, you get 0. So that one goes to 0. It's got just as much positive area as negative area on the other side. And I can use the formula to calculate the normal V. Anybody want to hear about 6? I mean, 6 is, it's just forcing you to, put eyes in places and calculate stuff with it, but there's nothing mind-blowing about it. It's just that this stuff is somewhat unfamiliar because I get the infinite sums, or I have eyes floating around, and maybe I'm not so used to dealing with eyes. In quantum mechanics, every day, 100 eyes, right? Eyes are all over the place. Good. Other questions on that? Other examples you're thinking of before we just do a last bit of discussion here? Let me get me off the screen and go back to my stuff. We'll talk about one more concept here. What's going on? So it does not like that I'm holding that. Ah, there we go. Complete collection of vectors. So this means, as we know, complete means you have enough of them so that you can build an arbitrary thing as a linear combination of things in that collection. So if we have a discrete collection of vectors, that's one case we're going to talk about, it's going to be called complete if any other vector in the vector space can be written as an infinite linear combination of those. Or if we're in a finite dimensional vector space, it might be a finite linear combination of those. We've seen examples of those, or at least the components of those, back in chapter 2. Now, there's something to be a little bit careful about here, and I added a note because it isn't in my notes. If we have a vector space, an ambient vector space. So here I didn't say what the vector space is because I'm sort of talking in the abstract, but suppose we're talking about little L2. When I say a vector, think of a vector. We have some ambient vector space we're around. It should be an element of that space. So in this case, when I say a collection of vectors, they should be all elements of the vector space that we're talking about, right? So if we're talking about square integrable functions, then if I say I have a complete collection of square integrable functions, for example, if we take the simple harmonic oscillator energy eigenfunctions, I'm going to label them just as psi n. N goes from 0 to infinity. So there's an infinite collection of things. If the vector space we're talking about is capital L2, all of these are in capital L2. They nicely fall off like Gaussians as you go off to infinity. Certainly if you square them, they also fall off like Gaussians. And so they're perfectly square integrable. So these things exist in this vector space. So in this case, when we say a collection of vectors, they should be elements of the vector space. Now, why am I emphasizing this? Because we're about to see an exception to that when we talk about a continuous collection. We're going to say a continuous collection of vectors. Here, I'm thinking of VK. K can be a continuous parameter going from minus infinity to infinity or something like that. If an arbitrary vector in the vector space can be written as a linear combination of those. Now, if we're considering the space of square integrable functions, the definite energy eigenstates are not square integrable functions. And so in this case, I might be tempted to say, you know, I'm thinking of, let's even take the Dirac orthonormalized versions. For a free particle, we said, you know, any square integrable function can be built out of this continuous collection of functions. Yes, that's true. But if we're talking about our ambient vector space is the set of square integrable functions, these are not vectors in that vector space. And so usually when people say vectors, they mean a vector in whatever vector space you're concentrating on. That's your world, your vector space. And in this case, these are not elements of this, and so it's questionable whether you should be calling them vectors. Nonetheless, physicists usually do, so we're going to still sloppily refer to things that are outside the original vector space, but out of which I can build up things that are truly in the vector space, right? I can take these things not lying in this vector space, and I can build up any element of this out of these more general collection of things. They are vectors in a larger vector space. They're just not in our original vector space that represent physically meaningful states in quantum mechanics. Okay, what about an orthonormal basis? That's an orthonormal basis is more than just an orthonormal collection, right? I could be in an infinite dimensional vector space and say, here's 3 functions. They're all normalized and they're all 3 orthogonal to the other 2. So it's an orthonormal collection, but we don't call it a basis unless it's also a complete collection that's orthonormal. So it's got to be legitimately a basis for the space so that I can write any other thing out of it. Okay, so any true orthonormal basis is going to be discrete. Because if I have a continuous collection, we're always going to find that those vectors don't lie in the original vector space that we're talking about, right? If I have a continuous collection of vectors and I want to build a square integrable function out of it, these things that I'm building, if they're a continuous collection, are not going to lie in there. And so it's always going to be a discrete collection if we're talking about capital L2, if it's a true orthonormal basis. But if we've got our usual Dirac orthonormal bases, we're going to say basis vectors in scare quotes, you know, just to say they're not really vectors, but they're vectors in some larger vector space. You got to understand that when we say vectors, that we're using it in 2 senses. There are 2 vector spaces sitting around. Okay. Yeah, let's just talk about this. If you take, has anybody taken real analysis here? Any math double majors? Huh? Oh, okay. Well, so you'll talk about what does completeness mean in a vector space. So we need, here's a definition. You don't need to know this for this course, but just so that you've heard it one time. How do we show that something is complete, or what does it mean that a vector space is complete? Well, in order to say something about completeness, we need to know the distance between two vectors. And the distance is defined somewhat intuitively, right? If I put the tails of two vectors together, so here's maybe vectors lying in the plane. Here's vector v, here's vector w. I put their tails at the same location. I say, what's the difference between these? Oh, what I mean by the difference is just how far between the tips. So I could calculate a vector v minus w, which geometrically goes from one arrowhead to the other one, right? And the distance between these two vectors is just going to be the norm of that difference. So we're building things up, right? We had an inner product. We built the norm out of the inner product, and now we're getting a distance function out of the norm, right? All these things are kind of built on each other. There are other ways to do it, but this is the most common way in physics. So we got a distance function between vectors. I can say when vectors are really close to each other or they're really different, they would have a big difference between where the tips are if you put the tails at the same location. There's a definition of something called a Cauchy sequence of vectors, which is a sequence of vectors in which the distance between pairs of vectors in that sequence it gets smaller and smaller. So a Cauchy sequence of vectors means if you take, say, adjacent vectors in the sequence, the further you go down the sequence, the closer they should get together. But it's more than that. You tell me any distance epsilon, no matter how small, any finite non-zero epsilon value you specify, there should exist some index capital N such that the distance between any two vectors I pick in the rest of the series, no matter how far apart they are, I say, okay, if N is 50, you say, let epsilon be 1/100th. Okay, that's a really small epsilon. Suppose it's true that if capital N is 50, that means if I take I've got an infinite sequence of vectors. If I take any two vectors past the 50th index and calculate the distance between them, it should be less than 1/100th. If that's true, no matter what epsilon you choose, that's called a Cauchy sequence. So a Cauchy sequence of vectors is a sequence of vectors that are getting closer and closer to each other in a very specific way. They're not only getting closer and closer to each other in an adjacent sense, they're getting closer and closer to all the ones further on from them in the sequence. Okay. So a vector space, we're going to say, is complete if every Cauchy sequence of vectors converges to a vector in the same vector space. The best way to understand this is to see counterexamples. What is a vector space that's not complete? Here's one that's not complete. Continuous functions of x. Let's say real continuous functions of x. That's something we're all familiar with. It certainly is a perfectly valid vector space, right? We talked about that in our example earlier, right? I can take linear combinations of continuous functions. Any finite linear combination is going to be still continuous. You can define the usual inner product on it and get the associated norm and get the associated distance function. There's a lot packed into that sentence. It's not a complete vector space in the sense that here is a sequence of continuous functions. They're going from 0 to 1 in a linear sense, but they're going from 0 to 1 as you go further out in the sequence. They go up to 1 faster and faster and faster, and they're sort of approaching a function that is discontinuous, right? See how that, if this is 1/2, and then it's 1/3, and then it's 1/4, and then it's 1/5, those functions are going to go up to 1 more steeply as I go further out in the sequence. So the sequence looks like, let's just draw the first few of them. Here's n equals 1. This is, what am I calling these? F1. Here's a graph of F1 as a function of x. It goes up to 1 like that, and then stays 1 forevermore. Here's a graph of F2, 1/2, 1/2. It should go up to 1 that fast and then stay there forevermore. F3, 1/3. It goes up there and so on. F100 is going to be almost vertical, not quite. It's approaching a function that is discontinuous, and that's not in our original vector space, right? Our vector space we're talking about is continuous functions of x. This is a Cauchy sequence. You have to think a minute to actually define that, but the norm defined from the inner product that looks like this and the distance function associated with it is going to tell you that any function, you know, past 50 is going to be really close to all the other functions in the sense of the distance function that we're defining here all the way out. Important for us is that, sorry, I put this 2 downstairs, but it should be upstairs. Capital L2, the set of square integral complex functions of a real variable, is complete. So for us, that means if we're writing down infinite, well, I'll tell you what it means perhaps next time. But let me give you another example of something that is not complete. How about the set of, I want to define a vector space. My vector space is going to be the set of all rational numbers. Like every vector in my space is a rational number, right? Can I take linear combinations of them? Yes, I need to tell you what the scalars are. Let's say the scalars are real numbers. And so the vectors are, if I take a linear combination of 2 rational numbers with real coefficient, with rational coefficients, I would need to use rational coefficients, then I'm going to get another rational number. The question is, so I can define an inner product on it, I can get a distance function. The question is it complete? Not surprisingly, it's not complete because I can find sequences of rational numbers that are Cauchy sequences. You know, you might think of, well, take rational approximations to pi. Pi is not a rational number, but I can make, you know, a fraction that's pretty close to it. What are some of the classic small ones? I'm forgetting. 22/7. Thank you. 22/7. You know, and then you've got one with hundreds up here and then thousands, and you're getting closer and closer and closer to pi. They're all rational numbers. And you could define it, you know, one way to do it is just geometrically take a circle and, you know, divide it up into a regular n-gon and find, you know, sum up the area of the sums of the lengths well, I'd have to think about it, but it would be easy to produce one, and not so easy, but you'd have to be a little bit creative. But I can take an infinite series of these, and they would get closer and closer and closer to pi. And you'd have to show that it's a Cauchy sequence, but in that case, that is not complete. That's why people don't like the rational number so much. It seems like, I'm not missing too much. There's not, you know, in between any two rational numbers, there's another rational number. It's almost like I'm not missing anything, but I am kind of missing anything. If I take these sequences, they zero in on nothing that's in the original collection. That's what we're trying to avoid with completeness, because we want to be able to, I think I just, maybe I'll say it next time, but we want, you know, it's going to help us define things like this. If this is a complete set of functions, and as long as these coefficients aren't too crazy, if they're square summable, then this is going to be guaranteed to converge to another square summable function, right? And of course, any finite linear combination would be square summable, but you got to be a little bit nervous as soon as you put that infinity there. A lot of crazy stuff can happen when you go to infinity, but this completeness of capital L2 is going to help us be reassured that these things actually make sense. As long, you know, these C's can't be 1, 2, 4, 11. They got to get small pretty quickly. But if this is a square summable sequence, and these are all square integrable functions, this sum will converge to a square integrable function. All right, I know we did a lot today, but we're trying to get used to those definitions. I think it's a lot of fun